this is the outline of chapter 27. Okay, about the circuit theory. Okay, so the outline only include 4 items. So the first one is single loop circuit, and then the second one multi-loop circuits. Okay, so yeah, so I think it's more or less the an Ohm's law and something like the parallel resistance, something like that. Okay, and then we'll talk about the ammeter and voltmeter. Although you already use the ammeter and voltmeter in the lab section, but actually we will slightly talk about what is the characteristic of an ammeter or a voltmeter. And and finally we will talk about the RC circuit. Okay, it still consists of capacitor, but yeah, it's a first order differential equation. Okay, and then it is similar to the RL circuit. Actually, we slightly talk about it during chapter 30, but at that time I just told you that we are not able to I'm not able to tell you why the solution will look like that. But yeah, today I think I can really talk about the procedure to derive that those formulas. Okay, so here the single loop circuit, as you can see in the figure. Okay, I don't try to read through the whole thing. Okay, so actually the circuit is as simple as this. So a single loop circuit, which means we only have a loop, and then within this loop we have a battery, or we can say it is an EMF, the electromotive force. Okay, EMF. Okay, so this is nothing but a battery, and then it is in series with a resistor. Okay, so yeah, so it is really simple. Okay, so and then it also try to analyze it in the point of view from the power or from the energy. Okay, so actually it says if the dW is the work the device does to force positive charge dq from the negative to the positive terminal, then the EMF of this device is this case. Okay, so here we have a battery or an EMF. Okay, so it will have the work done on the dq. Okay, so positive dq. Okay, positive dq will go in this direction, or actually this direction is the same as the direction of a current. But actually, as you know, the charge, practically the charge should be some electron, okay, in opposite direction. So in this case, positive direction going in clockwise direction, or negative electrons or actually negative charge going in counterclockwise direction will be the same as in this case. Yeah, the only case that are different is the Hall effect we introduced in chapter 28. Okay, but here we can simply consider the charge is a positive charge and going in this direction, which is the same direction as the current. Okay, so actually this is the work dW. The dW is here, and then divided by this dq. This is actually the EMF. Okay, WQA. So you can consider this somehow like a voltage. So yeah. So in this case, the EMF and the voltage difference or potential difference is are similar things. Okay, so but actually here he tried to mention two concepts, or maybe a concept with 2 items. Okay, so here an ideal EMF device and a real EMF device. Okay, so ideal means 理想。 Okay, so actually in the real world it does not really exist, but yeah, if we assume the EMF device is ideal, it can simplify the calculation. So usually you use it. Okay, so an ideal device means it is one that lacks any internal resistance， 没有内电阻的，没有内电阻。Internal resistance. Okay, the potential difference between its terminal is equal to the EMF. Okay, so if we try to, let's say, measure the potential between this point and this point, okay, it is actually the same as the EMF. But if it is a real EMF device, it has internal resistance. The potential difference between its terminal is equal to the EMF only if there is no current through the device. So actually the circuit model for a real EMF is something like this. We have an ideal EMF series with a small resistance. Okay, so this is the model of the real EMF device. Okay, which is this one is ideal, but it is series with a small resistance. Okay, so you can simply imagine why it says like this. Okay, if there is no current, the potential difference between this point and this point, okay, is actually, so maybe we can say this is point A, this is point B, so this is VAB, and this is E, okay, this is E. So if there is no current, okay, if there's no current, that means the potential difference across this small internal resistance is zero, because V equals, let's say here, VR is I times small r. Okay, if I is zero, then this VR is zero. So which means that VAB will be the same as E. But if there is current, then this VAB will be smaller than this E. Okay. So that's the idea of ideal EMF and real EMF device. Okay, so here you try to consider it in energy method. Actually, when I study all the circuit theory during my bachelor study, I have not seen this method before. It will not be appear in any textbook of the circuit theory. So when I start to teach this course, so I somehow this is my first time to see this energy method. Although it seems like it is making things complicated, but it may be useful for later. Especially the next something in the chapter 31. So let's try to follow it a bit. Okay, so here it says, so here we have a charge going through this loop, and the charge dq will be I dt. Okay, so if you are not familiar with this expression, you can consider the definition of I is dq dt. So it's somehow like you just multiply dt on both sides, so we have a dq equals I dt. And in such a way, we have a dw equals E dq, okay, which is actually this equation. So we have a dw equals E dq and dq equals I dt. So here we have a EI dt. Okay, so this is actually the dw, which means the variation of the work done, or somehow like the energy. So from the principle of the conservation of energy, the work done by the ideal battery must equal to thermal energy that appears in the resistor. Okay, so actually we already know the power consumption of the resistor. Okay, if you remember, So actually the power consumed by the resistor should be let me see, P equals VI or I square R or V square over R or V times I for a resistor. Okay, so this is P, and actually dW is actually this power multiplied by dt, and this is actually dW P times dt. Okay, as much as this P is a constant, and then times the dt will be the energy. So this is the energy consumed by the resistor as heat. Okay, and then on the left side, it is actually this stuff, dW equals EI dt. I'm putting it here. So finally we just cancel dt on both sides, and then cancel this I and this I. So finally we have E equals IR, or I equals E over R, or actually it's nothing but EV equals IR. So actually this circuit is as simple as this, so we just need to know the V equals IR or EV equals IR. So using this energy method is somehow like what I said is making things complicated. Okay, so finally we have a potential method, which is like so here we try to introduce something called KVL. This is something like KVL, the Kirchhoff voltage law. Kirchhoff voltage law. Kirchhoff voltage law. And along with it, we also have something called KCL, which is Kirchhoff current law. Okay, so this is for voltage, this is for current. Okay, this is not the potassium chloride， 不是那个氯化钾，不是那个 potassium chloride， 这个是 Kirchhoff current law. This is Kirchhoff voltage law. So actually, we try to use KVL here for this single loop. So it is like we can try to start from an arbitrary point, and then we try to go through the whole loop, and then going back to here, it turns out to be 0. So this is what we have learned in chapter 24. If we have something like integration of E dot ds for a whole loop, this thing should be a 0, and this is negative v. Okay, v equals negative this line integral. Okay, so here we try to do something like this. Okay, so here we try to start from this point. Let's call the potential at this point VA, and then we go in this direction, going up. Okay, so this is negative, this is plus, this is minus, this is plus. So going through this battery or going through this EMF will give you a positive E. Will give you a positive E. So you should be familiar with how to determine the polarity. Okay, so if you are familiar enough, then you can determine this sign very quickly. Of course, this is E, this is IR, this is VA, but at the very beginning, you will be struggle to determine this whether it is positive or negative. Okay, so the idea here is for this battery, we go from negative to positive. Okay, so which means this is low, this is high, so we need to add E here, so that this point will be VA plus E. Okay, the idea is like this. And then going through here, this is the wire, so no potential difference. And then here, okay, we go through a resistor. So going through a resistor, the potential difference will be IR, and then actually this potential will be consumed by this resistor, which means that this is the source of the current, this is the end point of this current, at least for this resistor. Okay, so which means that for this resistor, okay, as long as the current comes from the top, okay, so which means that this point should have a higher potential. This point should have a lower potential, which means that, of course, this VR should be I times R for this point and this point. Okay, but actually we need to minus IR here. So this is higher, this is lower. So we need to subtract IR. Okay, so we're going back to here and then going back to point A. So this should be VA again. And then finally, we just simply cancel VA and VA, and then we move these to the right side. So we have a V equals IR or E equals IR. Okay. So the idea is somehow like this. And then, so here in the textbook, it just call it the loop rule, but in circuit theory, we usually call it KVL. We usually call it KVL. And then here we call it resistance rule, but actually it's nothing but the Ohm's law. Okay. I don't think we need to introduce more definition there, but we refer to the same thing. So it just makes you feel more confused. So I just tell you, this loop rule is nothing but the KVL, Kirchhoff voltage law, and the resistance rule is nothing but the Ohm's law, and the EMF rule is kind of still, but it's just this EMF. Okay, so the next case is like this. We have a real battery here. So just as what I said, we have an ideal battery, ideal EMF series with a internal resistance. Although this internal resistance is usually small, Yeah. Otherwise, if this resistor is large, then it will consume most of the power. Because if you want to put a battery here, you want this energy or the power provided by this EMF delivered to something you want. So you don't want this internal resistor to be large. But unfortunately, it always occurred, so we try to make it as small as possible. Okay, and usually the loading should have a larger resistance so that it could consume most of the energy provided by this battery. Okay, so here we try to do the same thing again. We start from this point, point A. And then one trick here is for solving the circuit is we always can define one point to be the ground. Okay, let's say we try to define this point to be the ground. Okay, we can use this to refer it as a ground, GROUND, or sometimes I just simply write GND as the ground, or sometimes I will draw it like this. It also refers to a ground. So it's just a circuit symbol, so nothing special. So some textbook will use this as the ground, and this as the ground. So both are okay. So let's say if this is a ground, so we don't try to put VA here, we just make it a 0, because finally VA and VA will always cancel each other. So we can just consider this is a 0 volt, and then we try to going also in clockwise direction. So here we try to go through this EMF, so plus E here, and then going through this small resistor R. Okay, so the direction is from bottom to top. Okay, so this is high, this is low. So going through it in this direction, we should subtract IR. Okay, we should subtract IR, and then going to point B, and then further going to this point, and then we should go through this R. Okay, of course this is a resistor, so we should subtract I capital R, and then going to this point, and then going back to the ground node, ground node here. Okay, so it should be equal to 0. Okay, so finally we just move these two things to the right side and then divide both sides by R plus capital R. So we have I equals E over R plus capital R plus R. Okay, so it means that for the real battery, this small r makes the current smaller, and actually part of the energy is consumed by this internal resistor. Okay, so for this figure, it's just try to flatten this loop into a straight line. So this is point A, this is also point A, referring to this point. So here, this is a battery. So you can see the potential VA, or we just consider it's a 0, goes up to E, and then when it goes through this small r, it decreases a bit by small IR, and then further go through this one, and then going back to the original VA or the ground. Okay, so here we also have the resistance in series. So resistance in series is nothing but the sum of the resistance. I think we already talked about it before. So I don't try to go through the steps. So the series resistance is nothing but the sum of the resistance. Yeah. So, but if you want to familiar with the KVL, you can try to do it by yourself. You just start at this point and then going in the clockwise direction. So this is a plus E and then minus all these three resistance like this. Then finally we'll get this expression. Okay, so for the series resistance in series, yeah, so it's nothing but the total potential difference. Okay, so it's nothing but the equivalent resistance. Equivalent series resistance is the sum of all the individual resistance. Okay. Okay, so next is so next we talk about to find the potential between any 2 points in a circuit. Start at one point and traverse the circuit to the other point. Okay, following any path and add algebraically the change in potential you encounter. Okay, so after you know the current, then you'll be able to find the potential difference between any two arbitrary points. Let's say in this circuit, we want to know the potential difference between point A and point B. So what we can do is like we start from this point A, VA, and then going in this direction. So it is plus E, okay, plus E, and then going through this resistance minus IR, and this point will be VB. And we can actually divide VBA to be VB minus VA, okay, which is the potential difference from here to here. Okay, usually I just denote it like this. I write VBA, and then a negative sign means this point, and then the plus sign means this point. So which means the potential at this point subtract by the potential at this point. Okay, so VBA equals VB minus VA, which means if we move these to the right side, it is actually E minus IR. Okay, so it's nothing like nothing but this. And so it mentioned the grounding a circuit here. So just as what I mentioned for when you solve a circuit, you can arbitrarily define only one point to be the ground. only one point to be the ground. You cannot define more. Okay, and then the power of the EMF device, is nothing but I times E, I times E, or I times V. Okay. So I times E or I times V is always correct for any electrical device, not only correct for resistor, but also correct for EMF device or other, or even for capacitor or inductor, yeah. Or even other non-linear device is also okay. Okay, so here we have a sample problem. Okay, which is really simple. So here it says the EMFs and resistance in the circuit of the figure A. Okay, figure A have following values: E1, E2, R1, R2, and capital R. What is the current I in the circuit? Okay, so yeah, so here it already defined the direction of I is like this. So here we can try to going this in clockwise direction. So let's say we start from this point B. Okay, so we go through the R1. Okay, so here we have a negative I R1, and then going through this EMF 1, the battery 1. Okay, so this is actually E1, so this is low, this is high, so here we should add E1, and then starting from this point going to here, and then the direction is like this. Okay, so this is high, this is low, so be careful. This one should be minus E2, and then we going further. Okay, so going through this R2, so it is nothing but IR2. IR2. Okay, and then next here we have R. Okay, so we also minus I capital R equals 0. Okay, going back to the original point. Okay, so here we just leave all this thing on the left side and then put all this thing on the right side. So here we have I equals E1 minus E2 over R1 plus R2 plus capital R. And then we can simply substitute the values. This is a 4.4 minus 2.1 all over 2.3 ohm plus 1.8 ohm plus 5.5 ohm. Okay, so this is nothing but 0.240 ampere. Okay, so this is pretty easy for the question A. And then for question B, it asks you what is the potential difference between the terminal of the battery 1. So which means that it asks you the potential difference or the voltage difference between these 2 points, let's say the point A and point B. Okay, let's say we try to find VAB, which means VA minus VB. Okay, so it will be something like you start from this point, you subtract R1, and then you add E1. Okay, so if you are not familiar with it, you can also start from, let's say, a VB, and then minus IR1, and then plus E1 equals VA, and then you subtract this to the right side, it is VAB. But if you are familiar, so you should know that this one, the difference between this point and this point should be like this battery, which is E1 minus IR1. Okay, so we already know E1 is 4.4, and then the I is 0.240 in question A, and then multiplied by R1, which is a 2.1. Sorry, 2.3, this one. Okay, so this is 3.8 volt, 3.8 volt. Okay, so here we talk about the multi-loop circuit. So here it introduces a term called junction rule. So actually this is nothing but the KCL. Actually we already introduced it in chapter 26, which means that the current going into a junction, the sum of the current going into a junction must be equal to the current sum of the total current going out of the same junction. Okay, so although this KCL is reading like this, but in my experience, I always try to define all the current are going in or all the current are going out, and then and the sum will be a zero. Okay, it will make things easier because if you try to define some currents are going in, some currents are going out, then you will be confused at some point, and then will make mistakes. So my experience is to define all the current are going in or going out for the same node. Okay, so here we try to analyze this circuit. So let's try to define a ground node first. So let's say this point is a ground. This node is a ground. Okay, so here this circuit is a bit more complicated. We have one loop, we have another loop here, and then we have one battery, we have another battery here, and then we have 1, 2, 3 resistor. Okay, so looking quite horrible. But actually this circuit is really easy. Okay, so let's say let me try to write out the solution first, and then I'll try to explain more things later. Okay, so here, so we try to use the junction rule. Okay, you try to use the junction rule to write out the current property. Okay, so here to write out the current property, we actually need some voltage parameter. Let's say we would define this one should be VB. This one should be VB. And if you are beginner to the circuit theory, okay, so student will try to define, this is VA, this is VB, this is VC, and then you try to write out Orthan's formula, and then many of them are dependent, and then they try to add and then subtract these formulas, and then finally they will make mistakes. So here, don't try to assume too many variables. For this circuit, we only need one variable. Why? Because if we define this is VB, then this one is nothing but VB plus E1. Okay, E1 is a known value. Okay, when you try to solve a circuit, E1, E2, R1, R2, R3 should be known values. Okay, so if this is unknown, okay, we try to add a known value. So this unknown value and this unknown value are depending on each other. So we only have one unknown variables. And then similarly for this node, if you define it, VC is one more, there will be one more variables. But actually this one is actually VB plus E2. So this one is actually VB plus E2. Okay. So in this case, we can write out the KCL or the junction rule at node B. Okay, so here we try to define all the current are going out. Okay, for this path, the current should be what? I1. How to calculate I1? I1 is actually, don't try to look at this. This battery won't tell you what current it is. It can be any current. or any amplitude or any direction. Okay, so even a battery look like this, the current can be going up, going down, or even zero. Okay, it is the direction of the EMF does not related to the current direction. Okay, so here for this current I1, we should determine by R1. Okay, so this is VB plus E1. This is ground. Okay, so I1 should be VB plus E1 all over R1. Okay, so this thing is actually I1. And then I3. Okay, so I3 is VB minus 0 over R. Okay, so VB minus 0 over R3. Okay, here it tried to assume I2 is going in this direction, but as I mentioned, I usually define all the current going all the way going out. Okay, so here I also try to consider this current is going outside, but here this is also an EMF. Don't try to determine the current related to this EMF. Okay, we should determine the current of this path by this resistor. Okay, so the voltage difference is VB plus E2 minus 0. So VB plus E2 minus 0 over R2 equals 0. Okay, so all these three currents sum up to be 0. Okay, of course you can still define, this one is going in, so it will be something like this current plus this current plus 0 minus this one putting on the right side. Okay, if you manipulate the plus or minus sign correctly, then it will be, you can still get the correct answer, but it will be, I think it will be more chance to commit mistakes. Okay, so so this is I3, and then this is the new I2 I define. Okay, not the original I2. Okay, so in this case, VB is unknown, all the other variables are known. So in this case, we have 1 over R1 plus 1 over R2 plus 1 over R3 times VB. Okay, and then all the other thing putting on the right side, it will be negative E1 over R1 minus E2 over R2. Something like this. And then VB will be negative E1 over R1 plus E2 over R2, all divided by 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so if you know all the values, you can just plug in and then you know what is VB. Okay, so for this circuit, if you know the value of VB, then you can quickly know what is VA. VA will be VB plus E1. VC will be VB plus E2. And then after you know all the no voltage, then you can also quickly find I1, I2, I3. Okay, so by substituting VB back to here, this is I1. By substituting VB back to here, this is I3. By substituting VB back to here, it is the new I2 or the negative old I2. Okay, so this is the idea of using KCL. Okay, so let's have a 10 minutes break.